All right, and so now let's continue on with number 6 as its own unique problem here. So we've got this wagon wheel. I don't know how realistic this is, but we've got, it says 6 uniform density rods from the center, each of length L. Each, we're considering that to be one rod, length L and mass M. The ring on the outside has a radius of L, of course, and it also has the same mass M as all 6 rods each. So the whole wagon wheel has a mass of 7m. And we want to find the total, the rotational inertia of this wheel about the center point. And so we saw that key word before, about the center. That means that we're going to choose that as our axis point. And the nice thing about rotational inertia is it's just additive. If I can consider this to be seven separate pieces, I can find the rotational inertia of each of those 7 pieces and then just add them up. And actually it gets even a little bit more simplified than that, because I could do this. I could say the total rotational inertia about the center is equal to 6 times the rotational inertia of one rod plus the rotational inertia of the ring. So that makes the calculation a little bit easy for us. Now let's start off by finding the rotational inertia of one rod. So maybe I'll make some room here. And you know, if we look it up on the formula sheet or somewhere, what we'll normally see for a uniform density thin rod is going to be 1/12 ml squared. Now, what's given to you there with the 1/12 ml squared, that is the rotational inertia of this uniform density rod about its center point. But that's not what we have here. For each of the rods that we have that we're considering, we're trying to find the rotational inertia of that thin rod about an axis point that's over at the edge here. And so what we need to do is apply that parallel axis theorem, which we've used before. But it's not too bad in this case. So let's make a little note here that this is the rotational inertia of the rod through its center. All right, or actually I'll just say center of mass here. Ooh. And what we want to find is the rotational inertia of the rod about the end point. Yeah, I'll just put an end here. The end point. And so our parallel axis theorem looks something like this. I need to take the rod's rotational inertia about the center of mass, and then there's this term that I just add in, m times d squared. This is what we see again on a formula sheet. So what we want is we want the rotational inertia of this one rod around the end point, and so we're going to take the 1/12 ml squared, and this is the mass of our object, which is at mass m. Now what does D represent? D represents the distance that we're shifting this axis, this parallel axis. We start off by having the rotational inertia about an axis that goes through the center of the rod. Now I want to find the rotational inertia about an axis that goes through the end point of the rod, so I need to shift it by that distance. Now the whole rod is length L, and so when I shift my axis from here to here, that distance is L/2. And we have to be a little careful that that is squared. Anyway, let's see what I've got here. 1/4 ml squared plus 1/12 ml squared is 1/3. This all adds up to 1/3 ml squared. And so I can just now substitute that in for each one of these. And now we can move on to our ring, which is actually a little easier, because when we look up the rotational inertia on our formula sheet for the ring, we're going to see we would see mr squared, where r is the radius of the ring. And in this case, the radius is just L. And that's, again, that's the rotational inertia of the ring about its center. But the center point is the axis that we're trying to find the rotational inertia about. And so we can just, that's it. And so we have 2 plus 1 equals 3 ml squared. So that's our answer, answer D in this case.